All right, here we are, a problem 1561 from the Engineering Mechanics and Dynamics, a 14th edition by RC Hibbeler. So we have block A and B. A has this velocity, and then we've been told this particular surface here, from this point to this point, this distance here of S equal to 4, there is friction. So we are being asked to determine how far this particular spring is going to compress due to collision. We can read through the problem. We've been given E, which is the coefficient of restitution. Okay, right. So what do you think this particular velocity will become just before it collides? Because of this friction here, we expect this to reduce. So the value we are going to find here is going to be equal to, or it will be not equal to, it will be less than this 10 meters per second. Right, because the kinetic energy due to 10 meters per second will get reduced due to the frictional losses experienced as this particular block, okay, slides or moves, slides over the surface, which has some friction, and just makes sense. All right, so we need to find this particular velocity just before it um, collides. And of course, we are dealing with impact, okay, and impact deals with a collision of bodies, right? So collision of two bodies over a short period of time, and then large impulsive forces are developed that interact with or between those particular bodies. An example is a hammer striking a nail. So then let's start with this. Let's say before collision, before collision, before collision, right? So what do we do before collision? The idea is to find velocity just before it hammers this before collision. So let's consider block A alone. Okay, so we're going to use the principle of conservation of, principle of work and energy. Right, so what do we have here? So we do have the work done from point 1 to point 2 is equal to the difference in the kinetic energy. All right, and here we are going to experience uh, friction forces in that direction, like so, okay, which will reduce the kinetic energy. Okay, so this one is our WA, which is just equal to MA G, and this is NA equal to WA. This is equal to 15 times 9.81. Here MA is just equal to 15 kg, and then MB is equal to 10 kg, right? And then this is our FK, friction force, which is just equal to mu K NA. This is just equal to 0.3 by 15 by 9.81, and this SCA is equal to 4. Okay, so this just, since this is in the opposite direction, we do have our reference in that direction, like so. This is our Y, this is our X. Therefore, this becomes negative FKS, which is just equal to half MA VA1 squared, VA1, I mean V2 squared minus MA VA1 squared. We do have values, so this just becomes minus 0.315 9.81 by 4 equal to half 15 VA2 squared half 15 10 squared. And therefore our VA2, this is just going to be equal to minus 0.3 times 15 times 9.81 times 4 plus 0.5 times 15 times 10 squared divided by 0.5 by 15 square root of that. So we do have 8.7439 meters. So this is the velocity here. Okay. So this is the velocity here. This is the velocity here. And we are saying this is our VA1, which is just equal to 8.7439. Alright, so once we found this, then we can now move on to the next step, which is after collision. So for this particular part, after collision, we are going to consider both block A and B. Alright, so we are going to use the principle of the conservation, since conservation is momentum is conserved, so say conservation of momentum. Okay, so say MA VA1 plus MB VB1 is just equal to MA VA2 plus MB VB2. Right, but we do know that this part here is 0 because our VB1 is equal to 0. So this is 0 because our VB1 is equal to 0. And what else? So we only have, and then we also know that our VA1, we just calculated it as 8.743, like so. Right. So writing this, we'll have a 15 by 8.7439, okay, plus 0 equal to 15 VA2 plus 10 VB2. Right. So we need to find this after collision. And then if we worked out this 7439 by 15, this gives us a 131.585 equal to 15 VA2 plus 10 VB2, and this becomes our equation 1, right? 131, 1585. So we've been told that our E, take E equal to 0.6, and this is just going to be equal to VB2 minus VA2 minus VA2 and divided by VA1 minus VB1, given that our VB2 is greater than our VA2. Therefore, 0.6 is just going to be equal to VB2 minus VA2 divided by VA1, which is a 10, minus VB1, VA1 is 8.7439 minus 0. Therefore, this 8.7439 times 0.6, this just gives us a 5.2463, and this is equal to VB2 minus VA2, and this is equation 2. Alright, so we'll go to the next page. I just need to collect these particular equations. So we have this equation here, and we do have the one here. So we need to solve this simultaneously. Okay, let me collect this. I collect this stuff here. Alright, let me create a page like so. Okay, here we go. Let me get rid of this. Then here we had a 15 like so. Right, so there we go. So solving this, solving the two equations. So we have, and write that as VB2 is equal to 52463 plus VA2, and therefore this one is 131, right? Let's go behind. Yes, so we have 131.585 1585 is equal to 15 VA2 plus 10 5.2463 plus VA2. Therefore, our VA2 is just going to be equal to, if we solve that simultaneously, we have 131.1585 minus 10 by 5.2463 and divided by 25. So this we get a 3.1478 meters per second. And let's check. So it's still in the same direction. So this is in the same direction like this. And therefore our VB2, just using this equation here, just becomes equal to, this we just sum it to 5.2463. And this gives us 8.3941 meters per second, and is also positive. All right, so we are not yet done. We just worked on the first part. So we are still working. There we go. So let's get back. So here the follow-up question is to determine the maximum compression of the spring due to the collision. Mind you, the block has collided with B. So before block A colliding with B, we are saying its velocity 10 meters reduced to 8.7 due to the friction forces, right? So this became our initial velocity for block A. And then considering the system of particles B and A, we use the conservation of momentum to find the change in velocities, right? So when we applied the conservation of momentum, we were able to compute the final velocities, right? Which are here. So VA velocity reduced further, or velocity for block B increased, and they were all moving in the same direction. So now the question is to find, so we have this system here like so, and then we have a spring, then we have a body, and this is block B, which weighs 10 kg, and it has this initial velocity. That we just calculated of equal to 8.3941. This becomes our initial velocity, and this spring has a stiffness of 1000 Newton per meter. So the idea is to find how far this is going to get compressed. And then here on the surface here we are assuming, assume no friction. Okay, so we're saying how far will this particular spring get compressed? This is what we have right now. So for this, we can use the conservation. We can use the conservation of energy. Okay, so we have T1 plus T2 is equal to, T1 plus V1 is equal to T2 plus V2. And our T here is just equal to half mv squared, and our V is just equal to Vg plus Ve. So T is kinetic energy while V is potential energy, and we have gravitational potential energy and elastic potential energy for mechanical systems, right? So we are looking at the conservation of or mechanical conservation of energy, or conservation of mechanical energy. All right, so again, so look at this. So this becomes our initial velocity, all right? Okay, so we are saying when this spring gets compressed, it will reach a point where it is maximum. At that particular point, T2 is going to be equal to 0, because spring has reached a maximum compression displacement. Okay, so T2 becomes 0 at that point. Then at this particular point, we expect also V1 itself to be equal to 0. V1 is going to be equal to 0. We don't have any gravitation because at this point, this spring is at rest, right? And then what about V2? So V2 will have V2G there is equal to 0. All right, but we do have our V2E just going to be equal to half k a squared. So we'll have that one. So let's write this. So we have half m mb v1 squared, okay, plus, so this is just going to be equal to half k s squared. So we have half, this is 10, right? And our v here is 8.3941 squared. This is equal to half by 1,000, and then we have s2 squared, right? And therefore s2 itself is just going to be equal to, this is just going to be equal to so if we calculated this, this is going to be equal to, let me check, the mass is 10, right? I'm sure this is 10 kg. So if we calculated this, then we have 0.5 by 10 by 8.3941 squared divided by 0.5 by 1,000, and then square root of that. Then we do have our displacement at 0.8394 meters. I guess this is the final solution, and this displacement is in this direction, like so. Okay, it's in this direction like so. All right, I guess this is about it. We have found the maximum, and this is the maximum. This is the maximum displacement. I have to emphasize this is the maximum displacement that the spring will undergo. So I hope this particular video was helpful. Of course, we started from here. We've done a lot of work here. Then finally we arrived at this particular point. So I hope this particular video was helpful. And if it was, give me a thumbs up, like my video, continue subscribing and sharing my channel. Bye-bye. And see you in my next screencast.